Good morning, everyone. Well, if Dynamo radicals would exist, then he could be your leader for that. Welcome on this Dynamo session for structural engineers. I'm Dieter Vermeulen. I'm working at Autodesk as a technical sales specialist for structural solutions in Northern Europe, so which means I'm traveling a lot through Scandinavia, Benelux, and UK and Ireland. And today I'm going to show you some workflow on how to use Dynamo in structural analysis, and I will try to teach you how to think differently on analysis and maybe step outside of our comfort zone and use other techniques for using structural analysis in specific situations. So by the end of this class, you should be able to understand at least how to generate complex models and how to use them, to reuse them even, in analysis software. And at the end of the presentation, I'm going to try to blow you away a little bit with genetic algorithms. So we will talk about Charles Darwin and introducing evolution theory into analysis. So I'm not going to show bugs or whatever flying around in here and show the evolution of the animals. No, we are going to apply it on analysis instead. So a little word about me. I have a 15 years experience in structural engineering. So I used to work for some engineering companies in Belgium. So that's where I live. I'm the author of Revit Beyond BIM blog, and also collaborate in our team blog, which is called BIM Toolbox. So if you want to get connected, I try to be as much as possible active on social media. So BIM for Struck is my Twitter name. Try to get in touch with me on LinkedIn, YouTube, or blogs. So any questions you have after the end of this session, or maybe this afternoon, sometimes you will get, I should have asked this question. Reach out to me and I can help you for that. Now, first, I want to start with a small question. Can everybody who thinks that they have a real good solution to have optimized designs in their workflow, can those guys or girls raise their hands? Good. I didn't want to see any hands, otherwise, well, it would be useless you sitting here then, of course, for yourself. The second question, would you allow artificial intelligence to reach that goal, to reach that challenge of optimal design? I'm not talking about ET phoning home or something, but like introducing computers to perform some specific work in your daily job that your brain cannot comprehend, not because you're not smart enough, but because we don't have capacity of doing it, we don't have time for doing it. Would you allow to do that? Yeah? Good. Let's look at this first image. When you want to design a chair, or you want to buy a chair, or just something with chairs, we tend to use some typical functional thinking on it. Like, I want this chair. I want a chair which is a little bit more like design, a designer chair, I mean. I want a metal chair or a wooden chair or whatever. In a second model, we would allow to have some specific fabrication technologies to make it better, to make it optimized, to lose some weight on that material. When we go on a third model, then we would allow artificial intelligence in it and try to think differently on it. So we would say, I want to have something to sit on, which has 4 supports, which has a specific height, which has some back support maybe. Now generate me something that is capable of doing that without even having to think about a function, about a chair. Then you would get this thing. Well, we could discuss about the aesthetics of it, but that's not the point in here. The point is that we would allow things like, we call it generative design, or we could use computational design to get to that result. Now, I see some of you thinking like, well, what the hell am I doing here? It's about chairs. I thought it was about structural engineering. I know. Well, therefore, there are plenty of other examples in our world that apply generative design, that apply computational design to reach a specific goal. Now, for instance, that one on the top left, that's my new biotype, the airport of Brussels. You might have seen already on the Innovation Forum the case of MX3D, the guys in the Netherlands that will print a bridge in steel using generative design technologies as well to get to that specific optimized design on it. Now, just a quick project description. The thing I'm going to use for the whole session, it's a virtual project we use in our team to present our solutions to our customers and to the channel partners. And it's about a train station. So we call it the armadillo roof from the Millennium Railway Station. So it doesn't exist. So if anyone in the room has some money and wants to invest to build this, contact me, yeah. Now, the thing is that this is an architectural design. The architect used a mass object, and this roof needs to have some structural support. So we need to build a structure underneath it, which will look like this. So spatial trusses, lattice truss columns, and all kinds of elements. But the thing is, the challenge in here is that the roof is a double curved surface. So if you look on top of it, you will see that we have two arcs at the sides, and if you look in front of it, you see another arc. So each of these trusses is unique. So which means if you have to change your design afterwards, like saying, I started with 6 meters between each truss, I want to change it to 6.5 meters, then you have to regenerate all these trusses or remodel all these trusses. So therefore we are going to use Dynamo instead to get that better working, to generate that for me, and if something changes, I will regenerate it. In the second part of the presentation, I will isolate one of these trusses and use it in analysis, because you cannot just design your structure, it needs to be analyzed, right? So we need to know which type of section to use for it. Are the stresses conform the specific code, Euro code or an American codes or the Asian codes or whatever. Now, this will be the specific workflow that can be followed. So first we are going to start with the structural model. Then I will make a structural analysis of that model using Dynamo again. Do some manual optimization, which will mean we are going to take one of these trusses and perform some manual operations to get a bunch of results out of it. And then we are going to touch that genetic optimization. So let the computer decide which kind of truss would be the ideal one for my solution. Now, the platforms that I'm going to use in here, you have to know in Dynamo there are two versions of Dynamo. We have the open source version, which is integrated in Revit. So if you have a Revit license, then you also have that Dynamo license, which is called Dynamo 0.9. But we also have a product called Dynamo Studio, which is exactly the same. So if some of you don't have anything of Building Design Suite or Revit and just have a license of Robot, then you don't have that Dynamo plugin working. So therefore you can use Dynamo Studio, for instance. So I'm going to show you both of the packages, and you won't notice any difference, because there isn't a difference. It's exactly the same product.
Is the Dynamo Studio open source, or
No.
is it the same version or functionality the same?
It's the same version, but it's not open source, it's licensed. It's a license model for it. Now, let's start with the first case, so the structural model. So first, I need to make a system. We are not going to model something. We are having to make a system. That's how we call it in Dynamo. And that system consists of lines. Those are the center lines, maybe, the positioning lines of the trusses and the columns. And then with some specific nodes in Dynamo, which are used to generate geometries in Revit. Those nodes will help us to create those lines, or to take those lines, I mean, and to generate structural framing and structural column objects in Revit. Now, I don't going to explain the basics of Dynamo, so I assume already that you know about it, or at least if you start using these scripts, so they're all available on the website where you registered for this class. So before you start using it, try to get up and running with Dynamo first, because it's complex to get to it. So it's not just like taking 10 nodes and then you have a truss. So I don't want to scare you off with it, so therefore some of you have already downloaded the handout I saw. So you will see that handout, I explained almost every node which is in it. So, but try to play with it and you'll see what happens, okay? Okay, let's go live for it. So this is the roof. This is the mass object. So like you see, if I go into plan view, you see how it looks like. So it's double curved in these planes. See? Now, from in there, from in Revit, I will start at Dynamo 0.9, right? Now, I don't have to install anything else, because when it's built in with Revit, then you have that specific connection, that binding connection between Dynamo and Revit. So you don't have to install any other packages for it. Okay, let's open up and go to the data sets. It's this one. So I made those scripts in a specific way that I can show you the results of each group of nodes. So I don't going to connect all the nodes, because you will have this. So it's people among you that like spaghetti. You have lots of spaghetti in here, right? So I don't want to connect them now, because it takes a little bit too much time in this presentation. I want to show you much more. So let's just do some specific basic parts first, which is the input. So the input I need in Dynamo is the surface of that roof, right? So I have to bind it into Dynamo. And we can do that using this node, the select face node. So I select that top surface of the mass. I run the script. There it goes. Then we get that surface in our Dynamo environment. Now this surface will be the basis of everything else that will be built up in Dynamo. So if you have a surface and you want to draw lines on a surface, then there are specific methods for it. So there could be plenty of other solutions for doing that. In my case, I decided to use a node called by isocurve. So an isocurve is in fact a curve that is working on that surface in a transversal or in a longitudinal direction. So if you need to have trusses like this, so in the transversal direction, I can choose the direction called 0. It's just a value 0 or 1. And then we will get those lines in here. Now, those lines needs to be divided. I mean, they have to be positioned on that surface. So we need an equal division on it. So what I tell to Dynamo in here is that I want to decide a number of trusses. So you could also change it to a distance, for instance. But in this case, I want to have a little bit more aesthetic design. So I want to have equal division of each of these trusses. Now, I say 18 trusses, then we make some kind of range, some kind of list on it, and then put it into the parameters, and then it will generate those lines on a specific position. So Dynamo will calculate that for me. Okay, let's run it. There it goes. So these stop lines, when I select the node, then I can see in blue which lines are generated by that specific node. So people among you that don't know Dynamo yet, and you want to start playing with those scripts, this way you can see what every node has been doing in that script. So you select it, and then you get a blue highlighted element in it. So these are the top lines generated. So because I chose 0 and 1, then we'll also get one at the edge. So that will be, like I call it, an edge truss. And these will be the middle trusses. Now, for the bottom chords, we also need those specific curves. So therefore, we can use an offset. And that offset will generate a curve that in any position you would draw a line which is perpendicular on that curve. It will represent the height of that truss. So in this case, I want to have a truss height of 1600 millimeter. Okay? So this is what curve offset is doing. So if I select this node, and you can see them in here. So let's switch off this face, because it's too dark otherwise. And then you get this. Now these are the bottom center line. I want to have a spatial truss. So you have to copy those lines again to the outside of these lines. So this is done by, well, I made it a little bit difficult in here by using a custom or by using a code block. You could also use functions like translate, but then I have so many nodes that I decided to have it into a code block instead. So it's exactly the same way of working. So this way you see a little bit different approaches of it. So that code block is generating then the real bottom chords, okay? Now, if you have a line And, or if you want to draw a line, from what is I'm finding the right words, how is a line made? What is the basic elements of a line? Exactly, 2 points. So the whole thing about this model is just generating points, connecting these points with lines, and then you have your whole structure. So every other group of nodes that are made here are exactly using that same principle. Generate a point, use those points to create lines, and that's it. So perform some list handling on it, and then you can take each second node or each third node or whatever, so that way it can help you to make diagonals, for instance. So let's see how this is done. So there is a specific node called curve_point_parameter, which will take the curve and it will generate points along that curve. Okay? So if I select this group, show all geometry preview, there it goes. There we have all the points. Now the trick is just connecting these points. It sounds simple. In fact, it is simple. It just looks a little bit scary because there are a lot of nodes, but there is a lot of geometry to model as well, right? So if we take this one, then we have our edge trusses, right? So what is these two nodes are doing? This one is just generating the vertical lines. This is generating the diagonals. So it's a custom node. It's just, if you double click on it, you can open it. Just a combination of some nodes to get diagonals. So it's also in the handout, or I mean in the data sets. You can reuse it in your daily job if you want to create diagonals, for instance. So it's a nice one working in that. Okay, let's close it. Now the diagonals for the inner trusses or the middle trusses are these guys. And then for the columns, exactly the same. But in this case, the challenge is I want my columns to point to, or to be connected at their base in one point, and then they have to go up and connect with 3 other points at the column heights. So therefore, I need to define where are the connection points at the base. So a line consists of 2 points, so I have to create a line somewhere and take those points and they will be the basis. So which line should I take? Well, those center lines from the bottom chords. Not the ones that are the real bottom chords, but this one, the positioning line. So take that line, pull it onto a plane, which is the base plane of my structure, and you get this. You get these lines. So these will, well, we can call them grids. These are the column grids. And the end points of these lines will define the start position of each column, so which will be this. The points create the lines. You have this, and I want to make lattice columns of it, lattice structures on it, so I need to generate points again. I need to divide them on that line, and then use those points again as a basis for new lines, which will be this group of nodes. The points, here you go, and then the column bracings. So it's each time the same principle, taking lines, making points on it, and reuse those points. So this means now, if something changes in here, if I, for instance, change the truss height to 2 meters, and run the script again, let's zoom out a little bit. You've seen it? Every element is repositioned because of that parameter. Now, if I connect this design with Revit, then I will have the same action, the same reaction of Revit on that. So making new trusses, or not making new ones, it will reuse the same ones and regenerate it. Okay. So now we have the system in Dynamo, which is this part. This left part is the system in Dynamo, and this will be the system in Revit. Now, why am I telling you this? Well, this part of the script, I will reuse it completely to make the same model in Robot. So if you have another package, another software package that can connect with Dynamo, you can reuse that and generate those objects in that other tool. Okay? Now, something very important to keep in mind when you're working with very large systems is that create a list of everything and try to discretize your list in a specific way so that you can identify each of those elements. Now, in Dynamo, it's possible by using a specific node called display by geometry color. So what I will do with this one, let's hide everything and run the script. Okay, a bit slow today. Now what it will do is take all the geometry and bring it into that color node. So we will get this. So that helps you also to identify each of your elements. To see, for instance, are all the columns nicely generated? Which are the columns, which are the trusses, which are the diagonals, and so on and so on. So it's an easy thing or a user-friendly thing, I mean, to get that identified. But something else that also is important is if you take your list, discretize it in a specific way in here, that you have the right order. That's very important for Revit. So Revit cannot handle all the data in one time. It needs to have some kind of logical order to generate each object in the good way so that it connects really good. So you know when you combine structural framings with structural columns and then using braces in it, then sometimes, well, those braces can jump around and go into the infinity, right? We want to avoid that. And therefore, you need to make that specific order. So I want to have the outer columns, then the top chords and the bottom chords, the roof strut beams, and so on and so on. So if you make that in this type of code block, then when the script will be executed, it will follow that order to execute everything and to generate everything. So now it's connected to some specific nodes in here, which will generate the columns and generate the beams and add also a specific type. So that family type should be preloaded in your Revit model. So otherwise you won't have any selection possibility in here. You should select the base level of those columns so that if you make schedules of it, that you know where each of the objects is identified. Okay, let's run it. And I just will generate here the columns and the beams, so we won't generate all the rest of it. So the principle is exactly the same. And you will see in Revit that besides the geometry, we will also see a preview of the Dynamo system. So the red elements are the structural framing and columns generated by Dynamo. And those blue lines are the system objects in Dynamo that are represented here in Revit. So if you would connect it with Revit, if you would generate an object, then it will be positioned like those blue lines are. Now, at the end, you get this result. So if something changes now in Dynamo, if I change the truss height, then it will change also in here again. It will regenerate. It won't create a new structure. It will regenerate the structure and reposition the objects in the right order.
But the element IDs, they remain consistent, right? So if you're hosting or you put embedded information in sort of structural elements,
Yeah.
you tweak it in Dynamo and update it in the geometry and whatever, or any of the other embedded data that was maybe added after the fact, is it all retained or does it recreate the structural number?
The Revit ID should be maintained, so it should not create a new object. So if a Revit ID has been, that's the way how Dynamo and Revit can communicate with each other. If you open the same script 3 days later and work again on it to regenerate everything or to make some changes. So in the background, it knows which Dynamo script has run on the top of it, and it will remember that Revit ID for it. Okay, so this is the first part. You know, let's, if it's okay for you guys, let's keep the questions at the end. I have 15 minutes left normally, so we should have plenty of time for questioning. Is that okay? Yeah? Good. Now, the next part of this presentation, let's close Revit. So we will leave Revit now and leave Dynamo in it. And let's have a look on structural analysis. You see, it's exactly the same one. So we will reuse that whole script and generate an analysis model instead. Okay? So let's go back to our live demo. So this is robots. Are there any robot users in here? Okay, good. And next to that, I have Dynamo Studio. Okay, so you see, it's exactly the same except for this part. I'm not connecting it to Revit. It's possible. So an alternative on this workflow could be that you start your model in Revit, you open Dynamo from in there, you select the surface in Revit, and then you generate your system and connect it to Robot. That's possible. In this case, I decided not to do that, exported the mass geometry from Revit to an SAT file, and then bring in that SAT file in Dynamo to reuse those surfaces. Okay, so I assume that the geometry won't change anymore by the architect. Not. Now, if you try the script at home, be sure that you reconnect the file from it. So the set file is positioned here at a specific place on my computer. So if you copy it, you have to reopen this one and then find the SAT file, which is called platformroof.sat, and then run it in here. Okay, let's just see if everything is disconnected. Yes, okay, that's good. Let's run it. There it goes. So you see, all of these are the same, so I don't going to explain this anymore. I go straight to this grouped node to preview it. So we have the system in here, okay? And if we want to continue now and bring this model into robots, therefore we need a specific package. It's a package built by one of our software architects, Emmanuel. It's called structural analysis it's just called structural analysis, the package. So if you go to the package manager, search for it, well, it's explained in a handout how to find the package and how to install it. It's really a great package. So it has been improved the last few weeks tremendously, and I could not follow anymore because it's so many things that came in. So I will stick only to the linear objects, but it's also possible already to generate panels. So if you have, for instance, very special curved surfaces and you want to make an analysis on it, it's possible using this package already. So you can generate that nice surface in Dynamo and bring it into Robot, but it's not, well, I will do something later on. People among you that follow my blog will see it popping up in the next coming months. Okay, so there are some specific nodes to create analytical bars, right? So that's what we need in Robot. We will make an analytical system which consists of lines and points again. So, good. Let's generate that. Let's bring that list into here and run. So now it will generate the whole structure. This whole thing will be generated in Robot. And afterwards, I will be able to assign sections to it. To assign boundary conditions, I will show you immediately, to assign the boundary conditions like the releases, the supports, the loads, because if my trusses change in positioning, then also the loads should change, of course, because I want to use the linear loads on it, right? Okay, let's see it. Let's bring this here, and this one there. There we go. Oh, that's a big foundation. It's better. So there it goes. It's already with the sections on it. Oh, too impatient, Dieter. There it goes. So, which is done by these specific nodes called assign sections. So, analytical bar, set section by name. You can get the name. Well, in this case, you will see that I used a lot of list get item at index. And the reason for that is that in a few minutes, I will show you how to optimize that structure. So, therefore, I will make all kinds of design options with all kinds of different section types. So therefore it needs to have a list input from all these sections and find section which is in row number 0, row number 1, row number 2, and make that design option, calculate it, get the results, and make your decision on it. Now, what is cool also about it is that you can load your sections already from within Dynamo. So you have to know in Robot, all the sections are available in databases, but you have to load them into your project. So in this case, I decided to do that by Dynamo. So if I want to change my design in a specific way, that I want to add some new specific sections, you can drop this one in this box in here, and it will load the sections straight into Robot. So you can use just a blank template file, for instance. Next thing is the boundary conditions. So the analytical nodes, which are these red dots, well, you cannot see them in red at this moment, but these guys here, they need to have a support. So otherwise the structure will fall down, of course, right? So it's a pin support. I want to have releases on it. And so pin fixed releases, pin pinned releases, so that we have a good structure, because otherwise it's completely fixed. We don't want to have a fixed model. It should be flexible, okay? On top of it, we have loads. So create the load cases. That's a typical workflow in robot. You have to create load cases first, and then after those load cases, you will create loads in that case, okay? So, which is this one in here. So these loads, it looks like a very complex code block, but it isn't. It's just lots of text in it to explain a bit on how this works. Now, since we don't have surface loads in the model, I need to think about how to position the loads on each of the top chords. So if you have a specific distance between all the middle chords, then which will mean that I have at the left side of the chord and at the right side of the chord, I have the panels which will be positioned on top of those trusses. And then at the edge, I will have half of that load. So this is what these guys will do for me. So I have a surface load. If I change this one, all the linear loads will be recalculated and regenerated in robot. And then at the end, and that's a very important one, it's described also in the handout. If you want to generate that analysis model, you should follow some rules. And the first rule is you need to bring in all the analytical bars into a list. You also need the nodes that are assigned with supports. You also have to bring them in, otherwise you cannot get the reaction forces on those nodes. You also need to bring in the load cases and then bring in the load definition. And the reason for that is that if we take that flattened list and bring it in the analysis calculate node, those data will be sent to a kernel, the robot kernel, to make the analysis. Although you would say, I see the geometry in here, so that's okay, right? So why should I take everything together again? Well, in the backbone, it will use that calculation engine to calculate everything that has been built up in here. So that's a very important rule to follow if you want to work with it. Otherwise, you will see that it will pop up with some yellow warnings then instead. Okay, let's calculate it, right? Run. You see, robot has reacted on it. It has calculated the model. Results are available. And then afterwards, you can take, well, I did take just one element, the first element, take that one, and give me the stresses in it. Give me the node reactions for the first node. Then we have this. These are all the stresses for each load case. So there are 3 load cases, one for self-weight, one for permanent loads, and one for the variable loads. Take these load cases and return to me the values of the stress in that bar. And for the same reason, I want to have the reaction forces of a specific node. So this is 38 kilonewtons. So let's go into the robot interface, go to the results, the reactions. There it goes. This is this reaction force. So you give something to robot, and the robot can give you back the results, which means that I can reuse those values to make my decisions, right? And these decisions will be the core part of our optimization. So now it's going to be very exciting. Let's start with the first thing. I need to have one truss. I don't want to optimize the whole structure, that's too much. So just take one truss. How will I decide which truss to take? Well, you will take the longest truss. That will be the most negative case. So try to find in Dynamo the curve with the longest length, and then take that index and then take that truss and work on that. So which means if I would reposition all the trusses by, for instance, saying I want to have 25 trusses instead of 18, then another element will be identified as the longest truss, let's say. Okay? So that will happen in that part of the analysis. Now, before you start with making optimization stuff, so before you start with making the optimization rules in Dynamo, a good rule is make your analysis as some kind of, or make your system as some kind of manual operated system. So which means I will bring in that Dynamo script, add some specific nodes to reuse the values and to change the values manually. So I won't let the computer interfere in that. I want to do it myself first. If that one works, then the one with the computer, with the generative design or the computational design, will work as well. So that's a very important rule to follow. Just first make your manual scripts, let's say, before you go into optimization. So now it's a little bit fake yet. At the end, I will show you how that optimization is really working. Okay, so let's go. Open the script. Go to the manual. This one. Which will be, again, exactly the same script as the bigger one for the whole structure, except the columns are deleted. You see there is no groups of nodes anymore in here. The columns are gone. And I just take the curve with the longest length and use that one. Just take that one. And then again, connect everything to the robot nodes, and you can analyze it and calculate it. So I won't run this script. It's exactly the same as the previous one, but it will just generate one truss instead. Okay? Then if that one works, and if your parameters up front in the system, if you change those parameters and you see it working in Dynamo and in Robot, then you can go to the next phase, which is the manual parameterizing phase. Well, I tend to call it something like parametric run or something like that. Now, what happens in here is that I made a custom node called the Armadillo Spatial Truss Analysis, which contains the whole project that I just showed you a few seconds ago. So you see, it's exactly the same, except for the end. At the end, the results that will be read will be different. I only want to have the maximum stresses in the whole structure, and I want to have the total reaction forces from the points for the case self-weight. So if I have those reaction forces, this means I have the self-weight of the structure. You hear me coming already? I want to find a structure which is as light as possible, where all the objects have stresses which are within the ratio domain, which are within the allowable stress domain, let's say. So therefore, I need to have those values. I need to have the reaction forces, and I need to have those stresses. So that's a specific part that has been added to that node then, so that you can get those results into a list. So a list will represent the maximum stress and the offset reactions. And finally, let's run it. Let's bring them to the left. See, this is a whole script. I will explain to you immediately what this will do. So what's happening in here is, again, taking that platform roof, perform some visualization in Dynamo for it, and here are my design parameters, which is truss height, truss width, the number of trusses, and so on. So let's run it. There you go. I don't want to have 2.58. I want something else. Okay. Let's take 2.3. Run. Yeah, works. Okay. Is the truss width working? Can test it again. So now I'm doing some kind of manual operation on it. And what it has done in here is something special. It has generated 3 models. So if I'm going to look into my browser in here, which is Armadillo, it's manual optimization. Let's take these ones. You see, I changed the values 3 times, so I get 3 models. So you can, afterwards, you can reopen those models and have a look on it. What happened if I change the truss height, if I change the truss width, and you can use that for further evaluation of your design. Now, this is a very important one to use if you want to go into optimization, because you need to have all these models. And also there is a thing when Dynamo is getting connected with Robot, it cannot change the structure if it doesn't have been saved into another file. So that's something typical in that API from it. So it should create each time a new file for it. Now, if we get those results, these are the results. Yeah. So I have for each. Yeah, these are the reactions, of course. So I have to go to that. Is there a watch note? No, there's not a watch note. So these guys are the reaction forces for each of the nodes. So there are 1, 2, 3, and at the other side also 3. There are 6 supports, so I get 6 values. If I sum all these values, then I get the total weight of that structure. Okay? So now these results are brought into some evaluation routine. And this evaluation routine, what it will do is it will take the values, it will convert it from Newton per square millimeter to Newton, from Newton per square meter to Newton per square millimeter, so that's just a simple calculation in here. It will convert Newton to kilograms because I want to have the weight, not the force of it. Then perform some summarize formulas on it, and then at the end you get a result in here, which are all the stresses in that structure. So there are 129 bars in it, so I get 129 truss results, which is the total stress for self-weight, permanent and variable in one time. So you could also add maybe some specific safety factors on it, but which I didn't do in this case. I just sum everything together and then that's it. Here is the weight. So the weight at this moment is 5,406 kilogram for that specific truss. So if I change the value manually, then this value will change also. Now, if you want to do optimization, you need to evaluate those results. And how can you evaluate them? Well, the first thing is that the stresses in the members should be lower than, in my case, 235 Newton per square millimeter. Okay? Second, I want to see if the weight is optimal. And how can you define if a weight is optimal? Well, in structural optimization, we give it a specific name, which is called penalty values. So you have a weight, and you have a weight score. And the weight score is in fact the actual weight plus penalties. And the penalties are assigned to members that, for instance, are overstressed. So if I have 10 members and the structure weighs 500 kilogram, and one member has, for instance, a exceeded stress, then the weight score will be 500 plus 1 times the penalty weight, which is in this case 1,000. So the weight score would be 6,000, and the actual weight, or well, 1,500 it will be, and the actual weight would be 500. So which means that the weight score is way over the actual weight. So I have to find a solution where the weight score is almost exactly as the weight. If you have an exact same value, then you have the most optimal structure that can exist. You won't find that probably, but you would need to find something which is very close. And therefore, I'm not a programmer. I tend not to use Python scripts, but in this case, I was forced to use that Python script. So it was like, oh, okay, oh, Python, oh. But I did it, and it worked well. So I won't go too much into depth in it. It's in the handout how it's working. But in fact, it's just handling all those values. It's finding a ratio. So the ratio is the actual stress divided by the allowable stress. If the ratio exceeds 1, then add that big penalty weight on it. If the ratio is lower than, for instance, 0.8, then I have an over-designed member. So that should be a better way to find another solution for that one. So there is also a penalty weight. But the penalty weight for the minimum, let's say for those ratios lower than 0.8, it's a very slow penalty, a very low penalty value. And the reason for that is I thought it was much more important to avoid overstressed members. You always have over-designed members in a structure. You don't want to have a structure with 20 different section types. You want to generalize a little bit, otherwise the contractor has too much work to do, okay? So therefore, you'll see it's a very low value, it's 50. So which would mean if we have those 10 members again, weight is 500 kilograms, there are 2 members which are over-designed, then I would have 500 plus 2 times 50, which is 600. Okay? So this is what the script will do. It will check all these values and then return me some very nice information, which is what is the original weight, 5,400. What is the weight score? It's 12,000. That's not optimal. It's not a good solution. I can tell you already, at the end of this presentation, we will see that the weight score will be around about 11,000. Yeah? That's because of some elements are over-designed, and if you have 100 elements which are over, or let's say 50 elements which are over-designed, 50 times 50 is 2,500. That early in the morning already. count it with that 5,000, then you get already to 7,500. So it's very easy to have a very high weight score if you have over-design in it. But yeah, we could not avoid it for that truss. So let's see this. How come we have 12,000? Well, there is one item which has a ratio which is 1.001. So that's an overstressed member, structural collapse. Okay, so therefore we have that 12,000. What about the ones that are which are not which are over designed, which is the list 0? You see, we have 120 members, 121 members that are over designed, which means their ratio is lower than 0.8. So 121 times 50 plus one time that overstressed member, which is 1,000, then you get to that 12,000 weight score value. That's the thing about that. Okay, now, if this one is working, you can use it manually, can manually optimize until the weight score is, well, an ideal one for you. But I don't want to do that. It's still manual work. I don't want to make those 100 design options in it. And therefore, we are going to use something else. Let's go into the structural optimization. So the first thing we need to do is, we need to keep track of time. First thing we have to do in here is a manual optimization. It's a parametric run. So the input in here will be a list of design options. So I want the computer to calculate if there are all kinds of trusses between 1.5 and 2.5 meter, for instance. Take all the specific truss heights, maybe with a step of 0.5 meter or the step of 10 centimeter or whatever. Create all these models, calculate them, return the results for the stresses and the weight, evaluate that with that specific Python script, and return the weight score. And besides that, I also want to use Excel for it. I bet all of you guys use Excel, right? It's the most used engineering tool in the world. So why ignore it? So let's use it instead, okay? So take Dynamo and connect Excel with it and export all these results to Excel, and then use some really fancy diagrams to see which of your solutions could be an optimal solution. That's where we are going to head for in this part. Where's robots? In here. So let's open my base file, my empty file, which is this one. And then go to Dynamo Studio. And let's open the parametric run demo file. So, it's exactly the same basis again as the one I just showed you with that manual optimization part. The only thing in here is the difference is just this part. It's, well, it's combining lists. It's a specific list handling method in Dynamo. If you have a function, so this is my function, my routine is generate structure, generate results, give me back those results. That's the function in here. And list combine will use that function as some kind of combinator and take the design option values, bring them into that function and perform a automatic analysis, some kind of iteration. So before I do that, I need to make my design options. So the design options will be something like this. Well, I won't generate those 100 models, so I just will do something like, let's say, between 1.5 and 3.5, and in here also 1.5 and 3.5, and generate something each meter, just 1 meter. Yeah? Want to skip it's a long process. It can take 20 minutes to generate those 150 models, but which is still exciting, right? 20 minutes for 150 models, but you don't want to see those 20 minutes, the robots running up and down, so of course. And so the 3 design parameters we have in here is the truss height, truss width, and also the sections, because I don't know which section to use. I'm a little bit lazy. I want robot to decide which section to use. Now, I have that list, which is this one. Take all these elements and generate design options for the truss height, truss width, and also with different sections. So if you want to, you can blow up your computer with 2,000 models maybe. So, but it has to make a little bit sense, of course. Okay. So I will, it's a list of yeah, it's a few. So I will only generate 2 options for that. Run it. Then we will see in here the design options. So all the design options I will have in total 26 models, which is too much yet. I only want to have less. I'll explain you in a few seconds. 17, it's too much. Not happy with that. Yeah, 7 models, that's okay. So we will have 8 models, not 7, 8 models. First model will be truss with 1.5 for the height, 1.5 for the width, and the section with index 0, which is the CHS 114. Okay? Then the second one will be 1.5 again, and then with another section, and so on, and so on, and so on. So we will have those 8 models that will be generated, 8 results that will be returned, 8 evaluations that will be made, and that can help me in making the right decision for what type of truss I should make. So therefore, I need to connect, of course, these guys in here to start the analysis. So let's bring those 2 guys next to each other so that you can see the process in the robot. Run. See, the model is changing. The loads are, well, the loads in this case are not changing. It are all times the same loads. But now it's doing it for a different width. It will use another height in a few seconds. It also changed the member types, so the section types, I mean. Well, you cannot see it very visual in here because the sections are close to each other. There it goes. Then you go to, in the meantime, you go to your disk and we go to the parametric run and you see all these models getting generated. So I set 8 models, so where am I? I have 8 models, so it's finished. Run completed. So afterwards I can reopen those models, of course, and see, was my calculation well performed? How come I get these results, and can check it afterwards to see what has happened in here. Now at the end, of course, I need those results, which are these ones. So I get a bunch of results. It's really, well, it's a heavy result thing I'm getting here. See? All kinds of stresses, self-weights, and so on, and so on. So let's evaluate it. So, well, there's a new custom node for that I made. It's just regrouping every nodes for that evaluation process. And it's a better approach if you use that with the custom nodes, because then that way you can perform list handling on the whole list of objects that have been made in here. And at the end, of course, I need to bring them in. There goes. And here we get a list of results. The first item is the weight. So my first design option generated a truss with a weight of 4,000. It has a weight score of 21,000. If I knew already that the 12,000 score was really, well, it was overstressing already for one object, then you know already, in this case, the few objects will be overstressed again. And you see in the 2, 3, and 4th index, the 2 is the percentage of overstressed members. So we have almost 10% overstressed. 90% is over-designed, and 0% is within the range between 0.8 and 1. So that first design option, it's crap. I cannot use it. Okay? So therefore, I need to make, of course, more design options. Yeah, I don't want to do this, like I explained you, it takes 20 minutes to get it. But you get that Excel file. It should have opened Excel already. No, it didn't. Okay, my file path is not connected yet. So again in here, if you try it at home, we find that Excel file and put it into the right position here with the browse. Run. And here I have my Excel file with all the data nicely stored in the right rows, in the right columns. And then, well, it's a better approach to evaluate, of course. You cannot evaluate with that watch window in Dynamo. It helps you to find intermediate results if your script is working, but you want to have Excel for that, using it. And then you can get those nice fancy diagrams which can help you make your decisions. So you can see easily that red is the weight score, if I'm right. Yeah, red is the weight score. Blue is the actual weight. So you can find the one with the actual weight which is very low, and with the corresponding part which has a weight score which is also very low. So this is only for 8 design options. Let me open up a file which I generated for those, I think it were 200 models or something I did. There it goes. And here you have that. It's not an earthquake, could be, but it's helping you making that decision. So now find the one with the lowest value in here and find the corresponding one with the weight score, which is lowest, and that's your optimal structure. That's your optimal solution. But again, it takes time. So you have to evaluate. I don't want to do that. I want a computer to do everything for me. So I just want to run, click on run, and then get a result which tells me this is the truss you should use. Okay? Well, let's go in there. Let's go into that field. Very good, perfect. Who knows this guy? Charles Darwin. Well, by coincidence, a few weeks ago I was in Paris with my family for a city trip, and we visited there is a museum there for the evolution of National Museum of Evolution History or something like that. And there is a floor which explains how the insects got, how they started to grow and during time, during the millions of years. And there were many quotes on the walls from Charles Darwin. And it helped me suddenly to understand the genetic optimization. It was like, okay, that's right on time before AU. Now I understand genetic optimization, how it works. And in fact, it's introducing Charles Darwin's theory into it and making natural selections and trying to find a selection which is the fittest one, which is the powerful one, which is the optimal one. And if you use genetic algorithms in your structural optimization, well, we have some kinds of protocol. There's some kinds of terminology we have to use in that. And the first one is the population. So we will have a population. You can compare it a little bit with humans. So imagine these are humans instead. It's very crazy material. We have a population, and each of them are encoded as phenotypes and genotypes. And the genotypes is like our chromosomes, right? Our chromosomes define how you look like. So if you watch in the mirror and you're not happy with that, it's because of your chromosomes. They have defined that. Well, with the trusses in here, the chromosomes are the data values, the truss height, truss width, the section index, and so on. So those are the chromosomes. Let's mutate that. Let's play a little bit. Let's massage that chromosome until I have an ideal solution. And that's what I will have with that fitness function. So any individual that is in here will be used into an objective function. So what is an objective function? It's that analysis model again, which generates that trust, generates results, make an evaluation on it, and that's the result, that's the objective. I want to have a result with a weight score which is as low as possible. That's my objective, okay? And to do that, it will take a selection. It will take one of the objects, or one of the individuals, take another one. So we will have something like a mom and a dad. We are making baby trusses. Those babies are put back into the society and look if they are fit enough. And after a few generations, it's like humankind, right? We also evolved. First we were walking like this, and then now we are 1 million years ago. We could not present stuff like this, right? So we have evolved in that. And therefore crossover and mutation algorithms are used to perform that specific thing. So, and then when it's brought back into that society, iterate over it, so generate, for instance, 5 or to 10 generations of it, and suddenly you will have a solution which is the fittest one, which is compliant with that objective I want to have. Now, let's represent a bit that problem. So what I will do in the next script is my objective, and if you perform structural optimization, it's very important that you write this down for yourself. What is my objective? Well, I want to have a minimal weight score. Okay, second thing, what are my design variables? Well, I want to change the truss height, I want to change the truss width, and also look at the primary members. Okay, change those ones too. Okay, you want to change them, and what do you want to do with those changes, in which domain? Because changing the truss height, that's very, well, it has to be constrained a little bit, otherwise you will have an infinite loop of your optimization. So you have to give it a domain, which is in this case a truss height between 1.5 and 3 meters. If it's bigger than 3 meters, then it doesn't make sense anymore because the architect won't like that. Okay? It's the same for the truss width. Oh, there's a little typo in here. It should be truss width instead of truss height. And the primary section index, well, I have a list of sections. Look through that and use all these sections I assumed in. But again, if you perform that analysis, there could be cases where all of the members, where 100% of the members are overstressed. Well, that's not a valid solution. I cannot do anything with it. So you have to put constraints in your optimization, which we've done already in our manual optimization. I put in constraints with those penalty values. These are the constraints. I tell to Dynamo that find solutions which have a ratio between 0.8 and 1. All the others are not good. Try to find that one. And if not, then use that penalty value, that 50 kilogram, and that 1,000 kilogram. So these are the constraints. So you have 4 important things: objective, design variables, domain, and constraints. If you have those 4 things figured out, then you're ready for the structural optimization. So at the end, we will get this. I used a package for that, which is called Optimo. It's made by, well, the guy that now works for us, Mohammed Assel. So it's really, it looks a bit complex. It is complex. But if you get it, if you understand those 4 points I just explained to you, and you dive into that optimal stuff, you can really do, it's crazy what you can do. If you are in architecture, you can do optimization of your architectural design even if you want to. So there's plenty of examples of it already. Now, at the end, I will get this result, right? That watch note telling me that the ideal truss height is 2.33, 1.71 for the truss width, a specific section type that is used, and I get that weight score of 11,000, which is good for me. I'm happy with that 11,000. And with that parametric run I did, if you want, you can check if that result is also somewhere in there and find some more information about how many members has been overstressed. None, of course, because otherwise it wouldn't be an optimal solution. But you can look for the ones that are over-designed, and maybe you can track it afterwards in that Excel list. Okay, let's go into life with that. Now, I did that optimization already, yeah? So in this case, I won't perform the whole optimization in here. We won't find an optimal solution live in here. The optimal solution was presented in that PowerPoint. The reason for that, it took round about, I think it was like 45 minutes, and it generated round about, I think 300 or 400 models, and returning to me the ideal result, which was the one I just presented. So 45 minutes, that's quite okay, right, for optimization, okay? How does this thing works? That's a challenge. So again, the roof surface, bring in the load sections, so it's the same principle again. Making some constant values, so there are things that are not design variables, which are just the constant values. It needs to know how many trusses are you using along the length of that roof, so that it could identify the longest truss, of course. It needs to know the arc discretization, which is, well, I forgot to tell you that. If you have that arc, in robot, it didn't generate an arc, it generated lines It's discretization. So in analysis software, you don't get that curved object. It's a chained line, in fact, representing that curved object. So that's a discretization parameter that has been used in here for that. I also want to assign a directory where all the models should be saved, where they should be stored. So that's also important so that I can track down all the models afterwards. And these are my constraints. It's the same, allowable stress, the penalty weights, and the ratio domain I want to have. So I already have 2 of my 4 things. I have my design variables, and, no, I only have 1. Yeah, and my constraints. So my design variables are these ones, and the constraints, and these are my design variables in the domain, which is truss height, truss width, and again truss height, truss width. So I want to have within the domain between 1.5 and 3 meter. That's a domain where it should find the ideal solution. It's like I want to make a baby with blue eyes and blonde hair, for instance. It's a bit the same. That's your constraint you want to have. What is my objective? Well, this one, that's my objective. That's my objective function. It's the same function we used for that parametric run, yeah? And it returns me the weight score. So that's my objective function. How many objectives do I have? Well, in this case, it's 1. I can blow you away with examples of multi-objective optimization, so which means that it has multiple objectives to reach. So, and then you have to find an optimal result. We call it the Pareto front result, right? So, but we are not going, maybe that's something for next year, right? Not. We have to assign a number of population. So we have to start with, let's say, Adam and Eve, yeah? And we have to know how many of them should start. So I decided to start with 10 people, 10 specific trusses, and work with that. Work with those guys and make babies of it and make a few generations, and those few generations are the iterations. So in this case, it's easy to count. You have 10 populations, 10 iterations, so it will return 100 models. Yeah? But 10 iterations are 10 generations, so grandfather. All right? Now, we won't do those 100 models, so I will just do 3 iterations for, let's say, let's start with a population of 5 people, okay? Now, that's my design variable in here. What are these guys doing? Well, that's the Optimo stuff. That's a genetic algorithm. So the first one is this here, the assigned fitness results. So this one will take that objective function and it will calculate it. So it will run that specific function and it will allow us to take all the design variables, bring it into that objective function and return the results, and it will make a specific list on it. So let's just generate something already. Let's run this one. What it has done now at this moment, this is the population which we will use to start. So those are the first elements in the optimization. Truss height 1.8, truss width 1.6, and the section index, well, I will use some rounding to find the lowest integer, so it will be section index 1. And these values are the weight scores, so it's a placeholder. So of course I didn't do any optimization yet, so I don't have weight scores, so those values are equal to 0. Okay? Now in the next thing, in that assigned fitness results, it will take all these values again, and this one will be filled in with the weight score. So it will be replaced by the weight score instead. So that's what these guys are doing. In fact, if you're trying to use it yourself afterwards, the only thing you have to do is make that specific function and connect it to this node. And don't touch these ones, just leave them, and you will have your genetic algorithm already. If you want to dive more into depth and want to understand more of it, then you can go into this one, which is the NSGA function. So that's the natural selection genetic algorithm. And this one is a guy making crossover and mutation. And this one is Charles Darwin sorting out which one is the best one. Okay? So these, well, it's very complex. I don't want to dive into that at this moment. So I just want to show you the concept of it. Okay? Let's run it. Run. Meanwhile, I go to the GA optimization. And in here, we see all the models that started creation. So I will have those 3 times 5. I will have 15 models at the end. And I will get a result. I'll explain you immediately what that result will mean. So give it some time to run in here. So what it is doing at the moment is it's taking all these values. The results are returned, so that weight score. Then the genetic algorithm sees that the weight score is not optimal. It's not the lowest values. So it makes crossover and mutation between the initial values and generates a new truss height value, brings it back into that calculation, and by result it makes a new model. So it's not me deciding to find a value between 1.5 and 3 every 10 centimeter, for instance. No, it could be something like every 1 centimeter or even every half centimeter, right? That's what the genetic algorithm is doing. It's deciding itself which value to take and then brings that back into the results population. So meanwhile, it's almost finished. We have 11 models already.
Is it always decided based on the most fit selection at every step, or some of it random?
I will bring you the microphone. I didn't understand you very. Oh, there is no microphone in here. Okay.
At every step, does it always select based on fitness, or is there ever sort of a random seed?
It starts randomizing. So the first values that were generated are random generated in between that domain, and the mutation is taking 2 of those values to generate a new one and evaluating it with the objective function to see, is the weight score low? No, okay, you're done. Next one, is your weight score low? Yes, okay, we can build further on that value. We have first value, second value, randomize in between, and make a new generation of those guys. So, and at a certain moment, you will get design options with all the values that are equal. So for instance, my population of 5, I will have 5 times the same truss height. If you get to that result, then you know you are in your optimal, in your Pareto front optimal. So that's what is going to be shown right now. It's finished in the meantime. These are my results. So what I get in here is well, it's more or less optimal. Yeah, it's a new solution I got in here. So I get a solution of 1.6 for the truss height, 1.98 for the truss width, but unfortunately the sections are not, well, yeah, they are. Okay, I'm surprised a little bit. I have an optimal solution with this one too. That's good. You see the sections are 3.15, so this means that all the values are the same. If your optimization didn't work out, then all the values are different. If you have all the same values in each of those population, which is between 0 and 4, then I have an optimal solution. Well, optimal within the population I made. So my population was very small. Normally you should start at least with 10 and make at least 5 generations. So which would mean I would have 50 solutions. You would see if I run this one 50 times, then I will have variety of results, which means that I wouldn't have found an optimal one. So therefore, you can evaluate that weight score. So if I wouldn't have done anything else with that parametric run, for instance, then I would say, okay, this is my optimal solution, let's build it. But the weight score is 15,000, and I know that there are solutions with a weight score of 11,000. So this is not an optimal solution. It's just because I took such a small population, just for this purpose, for the presentation. So keep that in mind, use a big population to start with, at least 10. Yeah? But this one is just trying to test it to see, is it working, yes or no? Because you can also get results like null. So no values. Then it means it doesn't have worked. It doesn't have generated any of the elements because your domain was maybe not set or your variables were not okay, or your script function is not working. So that's also a problem